Welcome to Calc 3. We're gonna just get started and hit the ground running. Our first section that we're gonna cover in this course has to do with vectors in the plane. So that's vectors in 2 dimensions. For some of you, this will be review. If you've taken a physics class, or maybe in your trigonometry class, you had to deal with vectors. And we're just gonna kind of quickly overview what are some of the basic ideas behind vectors, so that we're all on the same page starting this class. So first of all, a vector is a directed line segment. So it has a direction, and I've tried to draw an arrow there. It has an initial point that it starts at, and then ends at a terminal point. So the vector I have drawn, vector PQ, we always write it listing the initial point first and then the terminal point. And we typically put these arrows over our vectors like I have shown right here. When I write vectors by hand, I always write an arrow over them. When I type them though, I put it in bold font. So if you see something typed in bold font in your textbook or in my lecture notes, that is also referring to a vector. Okay, so vectors have a direction, and they also have a magnitude, and the magnitude of the vector is the length of that vector. The notation that we're going to use for magnitude of a vector is these double bars right here. So that notation means magnitude or length of the vector, and the magnitude of a vector is just a number, a length. All right, a little bit more vocabulary. We often talk about our vectors in what's called component form. So the vector I have drawn on the screen, vector PQ, I can create, like I've done on the screen, kind of a triangle out of this vector. And we could say that the horizontal distance down here in yellow is my horizontal component. It's kind of like a very, very long time ago when you found slope, you talked about rise over run. So the run, the horizontal distance is my horizontal component. And then the rise or the vertical distance from my initial to my terminal component or terminal point is the vertical component of this vector. I'm going to use the notation V1, V2 for my horizontal component and my vertical component. Let's see, one more vocabulary word. We say a vector is in standard position if its initial point is located at the origin. So if we're asked to put a vector in standard position, it just means we're drawing it with its starting point at the origin. That would mean its terminal point would be V1, V2, where V1 and V2 are the horizontal and vertical components of that vector. Okay, so I've kind of alluded to this, but we frequently write vectors in component form. It's just a really convenient way of describing the horizontal distance, the run, and the vertical distance, the rise of the vector. And so when we write a vector in component form, we put it in these kind of triangular, brackets. And we always list our horizontal component first, and then our vertical component. So this vector in component form, V1, V2, again, using those triangular kind of brackets there. We can use this information to come up with an expression for the magnitude of this vector. So just simply using the Pythagorean formula, the magnitude of the vector is defined to be the length of the vector, this distance that I'm drawing in yellow. And so using my Pythagorean formula, my a squared plus b squared equals c squared, we can say that our horizontal component squared plus the vertical component squared equals our magnitude squared. And so the magnitude of a vector is always going to be the square root of the sum of our components squared. Again, that's just our Pythagorean formula written for vectors. All right, so that was a lot of notation, a lot of vocabulary. Again, I'm hoping some of it is kind of familiar, but let's actually do an example with numbers, and maybe this will make a little bit more sense once we put some numbers into it. So here's my first example. Given point P, which is at -1, 6, and point Q, which is located at 4, 5, we're going to put the vector PQ. And so the way I've written that vector, PQ, implies that P is the initial point, and Q is my terminal point. So that tells me the direction. Okay, so we are going to find vector PQ. We're going to put it in component form. And then this symbol right here is asking us to find the magnitude of that vector. All right, so horizontal component is just my change in x. My vertical component is just my change in y. And so change in x, I'm going to take my terminal minus my initial point, so 4 minus -1, and that gave me 5. So basically this vector is going from x equal -1 over to x equal 4. That distance is 5 units. So my horizontal component is 5. And then for my vertical component, I do the same thing, but with the y values. So terminal is 5 minus initial, which is 6. That gives me -1. So the vector starts with a y value of 6, ends with a y value of 5. That means we went down 1. So this is how I write my vector in component form. I'll circle it right there. In component form, my vector is 5, -1. That just means if I were to draw this vector in standard position, so starting at the origin, I would go over 5 units and down 1 unit, and that would be my vector in standard form. Okay, so then the second part of the problem says find the magnitude of that vector. And so to find the magnitude of the vector, we really are just using our Pythagorean formula, which says our magnitude is going to be the square root of 5 squared plus -1 squared. So we're taking the square root of the sum of our components squared. 5 squared is 25, -1 squared is 1, so I get square root of 26. And so that's the magnitude of my vector, or the length of that directed line segment. All right, here's another example. This problem says a vector v, and notice now I'm using that bold font to indicate that we're talking about a vector. That's something that your textbook does frequently. All right, so a vector v has a magnitude of 5, so we know the length of the vector. And the vector makes a 60-degree angle with the positive x-axis. Write the vector in component form. All right, so I'm going to draw a picture to help me with this. And then I'm going to have to use a little bit of trigonometry. So there's my vector in standard position. The magnitude is 5, so the magnitude is the length of that vector. And then the angle with the positive x-axis right here is 60 degrees. They are asking me to find my components. So if I kind of draw, a line here and create a right triangle, the distance that I just shaded in green would be my horizontal component, and then the distance I just shaded in blue is going to be my vertical component. And so this looks like a right triangle trigonometry problem, and in fact that's how I'm going to solve this. So I know that sine of 60 degrees would be opposite over hypotenuse, so V2 over 5, or vertical component over 5. So that means V2, my vertical component, is 5 times sine of 60 degrees. And let's see, sine of 60 degrees is root 3 over 2. So 5 root 3 over 2 is my vertical component. Same idea for my horizontal component. Cosine of 60 degrees would be the adjacent, so horizontal component V1 over hypotenuse 5. So cosine 60 equals V1 over 5. That means V1 is going to be 5 times cosine 60, or 5 times a half, or 5 halves. And so there's my horizontal component. So this vector in component form we would write as 5 halves, comma, 5 root 3 over 2. So same idea. I just had to use some trigonometry to solve this one. All right, that was kind of a quick overview of some of the basic ideas behind vectors. So on this next slide, I have a summary of all of the kind of formulas I've talked through very, very quickly. So first of all, let me just run through this and try to explain what I have on the screen. So a vector in component form, we always list our horizontal component, which is our change in x, and then our vertical component, which is our change in y. So that's the first thing I have written on the screen. That's just kind of reminding us that that is our vector in component form. If we want to find the magnitude of a vector, so that's the second thing I have written on the screen, we can use our Pythagorean formula, and the magnitude or the length of our vector will always be the square root of v1 squared plus v2 squared. The third thing we just learned in the previous slide, if we are given a magnitude and an angle, we can also write our vector in component form, just using our SOHCAHTOA or our right triangle trigonometry. The horizontal component is always going to be our magnitude times cosine theta, and our vertical component will always be our magnitude times sine theta, where theta is the angle that vector makes with the positive x-axis. Finally, the last thing I have written on the screen, I guess I haven't done an example using this fact, but the rest of that right triangle trigonometry applies to this picture. If I wanted to, for example, find the angle that a vector makes, I could use information about its components to do that, using the fact that tangent is opposite over adjacent. So tangent theta would always equal the vertical component, V2, divided by my horizontal component, V1. All right, so there's kind of a quick summary of some of the facts that we're going to be using when we talk about vectors in 2 dimensions, vectors in the plane. So the next thing I want to run through in this video is some basic vector operations. And so we're going to talk about 3 different operations. We're going to talk about scalar multiplication, addition, and subtraction. And so let's just start with that first one, scalar multiplication. So what I have highlighted, what this is saying, I guess first of all I should clarify that this word scalar, a scalar is a number. It is not a vector. So scalar is just a regular number like 5, pi, 0, just a number. It doesn't have components like a vector does. So this first thing, number 1, is telling us if we want to multiply a scalar times a vector, we can actually just distribute that number to both components of our vector. So for example, and so down at the bottom in blue, I have my example. Let's say vector v is 2, -1, and I've drawn that over to the right. So that means over 2, down 1. So there's vector v in standard position. If I want to compute the scalar 3 times v, this first property is just saying we multiply the 3 times both components. And so I end up with a new vector, 6, -3. And so I've drawn my new vector on the screen in green. And so multiplying a vector by a scalar isn't changing the direction. In this case, it's just changing the magnitude. It's just stretching it out, multiplying it by 3. All right, what about addition? So the thing I have highlighted, vector addition, u plus v, that formula is basically saying if we want to add two vectors, we just add their components together. So we add the x components, the horizontal components, and then we add the vertical components together. So for example, if I want to take vector u, which I'm going to say for this example is 2, 1, and I have that graphed on the screen in blue, so over 2, up 1. And then vector v, I'm going to define to be -2, 2, so to the left 2, up 2. So if I want to add these two vectors together, what this property is telling me is I just add the corresponding components. So I take 2 plus -2, and that's how I got 0. And then 1 plus 3 gives me 3. So the sum of these two vectors would be 0, 3. Now, there's actually a visual way to understand vector addition, and I've tried to put it into my screen. So let me actually go back a minute. So here's my vector u and vector v. And so one way of thinking about vector addition is you can think about, okay, we have this vector u. I'm going to keep that where it is. And then I'm going to take vector v and I'm just going to move it so that its initial point lines up with the terminal point of vector u. You can kind of think of it as like vector u describes maybe pushing an object in one direction, and then in vector v, now you're pushing it in the other direction. And so if you're adding those two vectors together, you're kind of thinking about, well, what is the net result if I move in the direction of vector u, and then after I'm done with that, then I move in the direction of vector v. And so that's what I have drawn in this new image. So vector u went over 2, up 1. And then I applied vector v. So from that terminal point on vector u, now I went to the left 2, up 2, and that took me to the point 0, 3. And that is where the sum of these two vectors ends, or that would be the terminal point of the sum of these two vectors. So what I have drawn in red is my sum u plus v. So the idea is if you line up the two vectors you're trying to add, and then create a new vector to basically to form a triangle, but the sum of those vectors has an initial point where vector u starts, and its terminal point is where now vector v ends, and the result in red is actually the sum of those two vectors. So it's just kind of another way of thinking about what we're doing when we're actually adding vectors together. Finally, for subtraction, we just subtract the components. So same example, if u is 2, 1, v is negative 2, 2. 2 minus negative 2 is 4. 1 minus 2 is negative 1. And there is the difference of those two vectors. All right, so putting this together, let's just do a quick example. If vector v in component form is negative 4, 1, and vector u is 2, 5, find u plus v. And then we're going to find 4v minus u. As you're watching these videos, if things are making sense to you, it's not a bad idea to pause the video, see if you can do the problems, and then check your answers after you try them on your own. But I'll just go through and run through this problem. So u plus v, we just add the components together. So I took negative 4 plus 2, that gave me negative 2. And then I did 1 plus 5, and that's how I got the 6. So negative 2, 6. For part B, 4v minus u, we are going to use our order of operations, so we're going to multiply before we subtract. So I started by finding 4v, and so to find 4v, I took vector v right here, and I multiplied both of the components by 4. So negative 4 times 4 is negative 16. 1 times 4 is 4. And then I subtracted vector u, subtracting those corresponding components. So minus 16 minus 2 is minus 18. 4 minus 5 is negative 1. And there's my solution. All right, one more definition. A unit vector is something that has the magnitude of 1. So a unit vector has a length of 1. So for example, if we're going to find a unit vector in the direction of v equals 2, negative 4, we basically just need to change this vector, modify this vector so that it has a magnitude of 1. And the way to do that is to first find the magnitude of vector v. So I did the square root of 2 squared plus negative 4 squared. I got square root of 20. So the magnitude of the vector given is actually root 20. If I want to modify this vector so that it has a magnitude of 1, I'm actually just going to divide it by root 20. So again, what I did here to find my unit vector, and here's kind of another notation thing. When we're talking about unit vectors, sometimes people put these little hats on top of it instead of arrows. Not always, but frequently, a little hat means we're talking about a unit vector. So to find the unit vector in the direction of v, I took vector v, and then I divided that by the magnitude of vector v. So I took 2, negative 4, and I divided that by root 20. And to do that, you just divide each component by root 20. And so there's my unit vector in the direction of vector v. You could simplify this further if you want, if this were on homework or a test. I don't care if you simplify your radicals or not, but root 20 is the same thing as 2 root 5, and then I guess you could reduce, so this would be 1 over root 5, negative 2 over root 5, and then if you really wanted to, you could rationalize and say root 5 over 5 minus 2 root 5 over 5. I don't care if you do that. This answer I have in green is perfectly fine. But sometimes it's nice to know that there's other forms the answer might take. Okay, we can kind of check and verify that this unit vector has a magnitude of 1. If you actually take, I guess I simplified a little bit, if you take horizontal component squared plus vertical component squared and square root it, you should get 1, and in fact you do. 1 divided by root 5 squared is 1/5. Negative 2 divided by root 5 squared is 4/5. Add those together, you get 1. Square root of 1 is 1. So this indeed does have a magnitude of 1. Okay, but anytime you want to find a unit vector, you can just take that vector and divide it by its magnitude. Now we've got two what we call standard unit vectors. Vector I is a unit vector in the x direction. It's the vector 1, 0. And the unit vector j is a vector that's in the y direction only, and it is defined to be the vector 0, 1. So those are just definitions. If you see an I or a j, vector I, vector j, it is referring to the vector I is 1, 0, j is 0, 1. So those are our standard unit vectors. And the reason I bring this up is because there's another notation that's frequently used for vectors. Vectors can be written in component form, and that's what we've been doing so far in this video with those kind of triangular brackets. Or the second thing I have written on the screen, so I'll circle it, this right here. We can also write our vector as what's called a linear combination of standard unit vectors. Or more casually, sometimes I just say, right, we can write our vectors with i's and j's. And so we write the vector as the horizontal component times I plus the vertical component times j. And it's just another notation. Sometimes the directions will be specific about the type of notation they're looking for. If the directions aren't specific, then I really think it's just a matter of personal preference. What notation do you like better when you're doing your work? So here's an example with numbers just to clarify. So the vector 2, 3 in component form. So if I have the vector 2, 3, so over 2, up 3. If I want to write that as a linear combination of standard unit vectors, I would write that as 2i plus 3j. So my next example says, find a vector with a magnitude of 3 in the direction of v, where v is 2i minus 3j. And this time they're actually telling us how to write our answer. Write our answer with i's and j's. So if I want to find a vector with a magnitude of 3 in the same direction as vector v, the very first thing I'm going to do is create a unit vector, a vector with a magnitude of 1 in the direction of v. So to do that, I found the magnitude of vector v by taking the square root of 2 squared plus negative 3 squared. So square root of 4 plus 9, square root of 13. So magnitude of vector v is root 13. And then we learned in the previous example that if I want to take vector v and write that as a unit vector, I just have to divide it by its magnitude. So I took vector v and I divided it by square root of 13. And that's how I got 2 divided by root 13i minus 3 divided by root 13j. So I divided both components by that magnitude. So that's a unit vector in the direction of vector v. if I want this vector to have a magnitude of 3, well, now I can just multiply it by 3. Because my unit vector has a magnitude of 1, to change that into a magnitude of 3, just multiply by 3. So I did 3 times both components, and that gave me my answer of 6 over root 13i minus 9 over root 13j. And writing it with those i's and j's is that linear combination of unit vectors. So that's my final answer. So this video was kind of a quick overview of the basics of vocabulary, notation, just kind of basic operations with vectors, as well as adding and subtracting vectors. We're going to do quite a bit with vectors in this class, but I would like to finish this video with doing an application, just to kind of illustrate why might we care about vectors? Why does having these arrows or these directed line segments, why is that actually important to talk about? So my last example is an application problem. It says forces with magnitudes of 500 pounds and 200 pounds act on a machine part at angles of 30 degrees and 45 degrees respectively. See figure. Find the direction and the magnitude of the resultant force. So vectors are used very frequently to represent things like forces or motion, because those are quantities that have magnitudes and directions. And so it allows us to do math when we have something with both of those quantities involved. And so in my picture, the little circle is supposed to be my machine part. And then magnitude of a vector, that's the length of the vector. And so the one on top, it looks like makes a 30-degree angle and has a length of 500 pounds. And then on the bottom of that figure, we have something with a magnitude or a length of 200 pounds. And this particular vector makes a 45-degree angle, I guess, below the horizontal. So I might actually say that angle is negative 45 degrees, just to indicate it's actually below the horizontal. All right, so what are they asking us to do here? They are asking us to find the resultant force, the direction and the magnitude of the resultant force. So I suppose one more vocabulary word here. Resultant means net or sum. So the resultant force, it would be the sum of these two forces. So basically this problem is asking us to add together these two vectors and indicate for the new vector we get, what is the direction and what is the magnitude of that vector. Now, there are multiple ways to do this problem, but I'm going to do it using the concepts we learned in this video. So I'm going to write both of these vectors in component form and then add them together. And so I'm going to start with the vector on the top of the picture. This is the one that I'm going to call vector u. So vector u has a magnitude of 500 and makes an angle of 30 degrees. So earlier we learned that we can write that vector in component form by taking 500 times cosine of 30, magnitude times cosine of the angle, and then the vertical component would be 500 times sine of 30. That's just using that SOHCAHTOA from one of those earlier slides. So doing some computations, I ended up getting that vector u simplifies down to the horizontal component would be 250 root 3, and the vertical component would be 250. So that's my vector u. We can do the same thing for vector v. So vector v is this lower vector. Magnitude is 200. And I'm going to say that that angle is negative 45 degrees because it's going down. So my x component is going to be the magnitude, which is 200, times cosine of negative 45 degrees. And then my vertical component is the magnitude times sine of negative 45 degrees. I do some math and I end up getting a horizontal component of 100 root 2 and a vertical component of negative 100 root 2. I'm glad that the vertical component turned out to be negative because I can visually see that that vector is going down instead of up. So now that I have both vectors written in component form, I can find the resultant force by adding them together. And to add two vectors together, we just add their components together. So I'm going to take 250 root 3 plus 100 root 2, and that'll give me my x component. And I went ahead and put that into a calculator, and I got this 574.43. And then for the y component, I'll do something similar. I'll take the 250 plus negative 100 root 2. I put that in my calculator and got 108.58. So those are the components of my resultant force. So now I have written my resultant force as a brand new vector. And so I guess the last thing I need to do is this problem is asking me to find the direction and the magnitude of that vector that I just computed. To find the magnitude, we know that we can take the square root of our components squared. So I took the 574.43 squared plus 108.58 squared, and then I took the square root of that, and I got 584.6 pounds. So the resultant force has a magnitude of 584.6 pounds. And then finally, the direction, angle theta. We can give the direction of a vector with respect to the positive x-axis. It's kind of how we describe theta in trigonometry and other math classes as well. And so if you want to find the direction angle of your vector, you can always take, I had it written on a previous slide, but I'll write it down again. You can always take tangent theta equals your vertical component over your horizontal component. Tangent theta is y over x. So I took tangent theta equals the 108.58 divided by 574.43. I'm going to have to use a calculator to solve this. So I used the inverse tangent button on my calculator. I took inverse tangent of that fraction. And I decided to put my calculator in degree mode, I think in this application, because all of the other angles are given to me in degrees. It just probably makes the most sense to answer this in degrees. And so I got 10.7 degrees. And so what that is telling me is that if you apply both of these forces on this object, the net result is you have a force that acts with an angle of, I guess, 10.7 degrees and has a magnitude of about 585 pounds. All right, that was my last example in this particular section. I know I ran through that fast. I'm kind of hoping that you've seen some vectors in some previous classes. But if you haven't before, that is perfectly fine. Feel free to let me know. I can definitely run through some of these concepts again in class if they're brand new, or if anything is confusing in the video, please let me know. I'd be happy to clear that up in class. So please let me know if you have any questions on this.